Welcome to a vector pathways example. The best way to truly understand vector pathways, I think, is to work your way through different examples and you'll start to see how the pieces fit together. I would like to draw to your attention what I said at the very start of vectors, is that although a vector can describe the shortest distance between 2 points. So U goes between S and P. That's the shortest way you can go between S and P. If you haven't got a vector for S to Q, you're allowed to describe it in terms of the pieces that make it up. So you can see here we've been given two vectors, and one of them is V and one of them is U. So let's look at V first. So V goes along the bottom of this square. And we think to ourselves, is there in any way another line in this shape that is essentially the same as the line between S, R? Is it the same length and does it go in the same direction? And what you will see is we also have P, Q. But we want to be quite careful about how we describe PQ, because we don't want people to think that it can just go either direction and it will be the same as V. For PQ to be the same, it has to be pointing the same way as vector V. Now, let's do the same thing for vector U. We have vector U goes from the bottom to the top of our shape. And we ask ourselves, are there any other lines in this shape that are really obviously also vector U? And you'll see on the other side, we have this vector RQ. And again, we need to make sure we're aware that when we say that vector is the same, that what we are saying is it also points the same way, because if it doesn't point the same way, it's not the same vector. So here we are. We have broken down our shape and highlighted all of the sides of our shape that are also vector U and vector V. I am not going to do ST first. I'm going to talk through another couple of examples because I think it's important we understand the underlying principles before we go straight in the deep end. So a vector can be made up of its parts. So going from S to Q is a vector. We've got our little hat on it. We're going from point S to point Q. And we have to ask ourselves, well, how can we get there? Using the vectors we know. And we have two choices. We're either going along and then up, or we're going up first and then along. And then along. Does it make a difference? Well, I've told you the answer is no, but let's think about actually in practice. So we have S to Q is going to be V, because you've gone along, and then up, U. So it's going to be V plus U. If you went the other way and you first went to P, then what we have is U, and then we go along, V. And they're not the same, or are they? In algebra, remember that if we have A plus B, that's the same thing as B plus A. And that's also true in vectors. It doesn't matter if it's 3 plus 2 or if it's 2 plus 3. You're both times going to get the answer of 5. So these are both the same. So that was a nice example. That example took us from point S to point Q without too much of a faff in between. Let's have a look at a different journey. What if I went from point P to point R? So point P to R. How could I make that journey? Again, we have two choices. So either we're going along to Q, which is V, and then we're going down to R, but we have to be careful. When we were drawing vectors, if we had a negative vector we were drawing, we went the opposite direction. So the flip is true, is that if you're going the opposite direction, you have a negative vector. So we have negative U. What about if we'd gone the other way and we first went down to S? Well, that would be P R is first negative U, and then we go along to R, positive V. And again, it doesn't matter which way round the negative U and the V are, you're still getting the same answer. You're still making that journey from P to R. So those are the basic ideas. You follow the lines you know around your shape to take you from the point you started to the point you finished. So let's go back to the original question. We had express S to T in terms of U and V. And the number on fact we need to notice is that T is in the middle of this square. We can't use any of the vectors we currently have to take us to T. But T is in the middle of lots of other vectors. So points, is in the middle of SQ. And what did we just say the vector SQ was equal to? We said SQ equaled U plus V. So we know this vector here. We have discovered it by calculating SQ. We have found an expression which we can now use to find T. And this is a really lovely trick we can do with vectors, is that we can take a fraction of a vector. So S to T is a half of SQ. So that's going to be a half of U plus V. So it's going to be a half U plus a half V.